Well, hello everyone. I'm Davera Gabriel, and I am going to be presenting, moderating this next session. Let's see, let me move this forward here. I'm thrilled to be the moderator, and we have so many excellent submissions that we don't really have so much time for them. So to make time to get this much good content in, we're going to be moving very fast today. And because time is so short, there won't be any questions, but you will have the ability to see these fine folks at their poster after this session. So get ready, stay sharp, fasten your seatbelts, because there's a lot of good content coming your way, super fast. My first person that's coming up is Polina Talapova, who will be presenting mapping of critical care EHR flowsheet data to the OMOP Common Data Model via SSSOM.
Hello everyone, my name is Polina Talapova, and it is a great honor for me to open the first lightning talk session. And before we start, I'd like to express my sincere gratitude to all the people who support my native country, Ukraine, during the full-scale war with Russia. Also, I would like to thank to the citizens and the government of the United States of America for the invaluable help, especially military help. Despite the enemy propaganda narratives, this support has been instrumental and clearly visible for us Ukrainians. And it's because of you that we continue our battle against the evil and the global terrorism embodied by Russia. Thank you so much. We do appreciate your help. And let's come back to the topic. So the topic is mapping of critical care EHR flowsheet data to OMOP CDM via SSSOM, or a simple standard for sharing ontology mappings. Starting with the background. So this slide shows the OHDSI's multifaceted journey. And you may see the real-world data, which is like Ouroboros, you know, this creature, and this symbolizes the endless cycle of data collection, harmonization, analysis, and evidence generation. As new data emerges, it feeds the cycle, promoting continuous research and discovery. Standardized vocabularies, old big turtle that you see above the real-world data, enabling us to utilize the data and interpret it. With the direction from the OHDSI leads, ETL translate data using the vocabularies, and the community, including software developers, utilize these resources, conducting studies and producing evidence that lead to more effective healthcare. So as you understand, the vocabularies as a core and the heart of the OHDSI ecosystem. That's why they are very important. So while various EHR flowsheet data requires mapping, our ultimate challenge is to define the best strategy for for generating, preserving, and disseminating mapping across the OHDSI ecosystem. And also we know that the health data mapping is costly, use case specific, and requires training and subject matter experts in healthcare. Also, it's essential for algorithm development and analytics. In turn, open source mappings usually do not have enough documentation and can lead to unexpected and sometimes hidden data inconsistencies. Also, we have adoption challenges because people use various sharing approach for mappings. For instance, source to concept map wide mapping table, staging tables, or lookup tables, and whatever have you. So that's why we have to take care of the OMOP vocabularies first. We need to support them to maintain the vocabularies, and also we need the enhancement in the area of provenance, precision, and mapping justification. So our solution is prioritization of the vocabulary usage and generating mapping precision metadata. So the SSSOM is the elegant solution for this, and it allows us to store this information and use it in our research and our ETL especially. So here you can see different metadata types like mapping origin and intent, mapping creation, mapping precision, and mapping entity, which gives us more details about mappings. The next thing that we offer is the usage of mapping metadata table, which can be added to the OMOP CDM. And this table contains information about the level of confidence of the mapping, shows the direction of the mapping, whether it's exact match, broad match, or narrow match, or related match. Also, we can see the mapping justification, whether it was manually created or automatically created. Also, we usually want to know who did it, who actually did this mapping, and this table can help us to store this information. Also, you may see reviewer ID and label, which can help us to see who checked and validated this mapping. Also, there is information about mapping tool version. For instance, Usagi or Jackalope can be there if you use it. The content of mapping metadata table should be discussed, and some fields can be added or excluded after the discussion. Next, it's the automation. So we are working on the development of machinery which can help us to integrate SSSOM mapping table into our ETL and our OMOP CDM instance. So we populate staging tables, mapping metadata tables, and this allows us to store information in basic vocabulary tables like concept, concept relationship, concept ancestor, concept synonym. And also we populate event tables using this machinery. Another important thing that we need integration of SSSOM into the OHDSI tools which do mappings or use mappings. And we began with Jackalope. The Jackalope is an AI-enhanced mapping tool which allows to manage mappings, create mappings, and visualize them. So if you're interested, please visit our another poster, number 24. The last but not least, and the most essential for us is the community engagement. That's why we encourage you to use mapping metadata in your ETL and in your current and future projects. So, yeah. If you do mapping or use mapping, please visit our poster 501. Thank you very much for the attention.
Next up, we have Theresa Burkard, who will be presenting Paving the Way to Estimate Daily Dose in OMOP Common Data Models for Drug Utilization Studies in DARWIN EU.
Good afternoon, and welcome to my presentation on dose estimates. I would really like to thank the organizers for giving me the opportunity to present this work here today. And I can assure you we've worked very hard these last couple of weeks and months. And with that, I will not only show you the dose finding approach, but also some dose estimates as well as validation today. We think that drug dosing is very valuable for pharmacoepidemiologic studies because it has a lot of applications. However, it's quite a challenging task. Some of you who've tried will agree with me. And especially in some databases, you don't have the dosing available that the doctor may have prescribed. However, there is quite an excellent reference, which is the WHO ATC Daily Dose Index. And here you see the example of paracetamol, which has a kind of a standard daily dose of 3 grams. And there is different administration routes. It's oral, parenteral, or rectal. And it's actually those dose forms, those different dose forms that gives us the headache when trying to estimate dose and finding dose formulas. So we set out to introduce a uniform approach to develop dose formulas, as well as validate those suggested dose formulas. Our approach revolved around units, routes, and the link with the OHDSI vocabulary is the drug strength patterns from the drug strength table. In detail, we identified 31 patterns with clinically relevant units, and we categorized them into 3 groups. You see the fixed amount formulation patterns, the time-based formulation patterns, and the concentration formulation patterns. And it's this last example which I want to use to show you the concept of how we derived the dose formulas. So here you see an example of 2 different patterns, and it's the numerator and denominator that makes up this concentration formulation patterns. In the first row, you see that the denominator is present, and in the second row, it is missing, which means it's a quantified drug. And in these concentration formulation patterns, we had 22 patterns with clinically relevant units. And to see what was really going on, we performed an extensive clinical review in 4 different databases, the CPRD, Gold, ORAM, the Dutch Primary Care IPSI database, as well as the Pharmetrics Plus for academics. And the suggested dose formula is depicted here, and the clinical review really wanted to know whether the numerator value made sense in relationship with the quantity. So we found that for the patterns depicted here, divided by root, whether this formula made sense or not. And if you want to know how we derived the root from the dose form, which is a separate project, you can find me at poster 13. So it's not only important to find or suggest those formulas, but also validate them. And we did this in using 5 different ingredients in 5 different databases, and we compared our estimates to the WHO daily dose. And for time constraints, I can only show you a subset of results. So let's start with furosemide, which is 40 milligram in oral and injectable route. And this is a drug that's given regularly, so it makes sense to estimate those there. Okay. Let's see what's going on here. Okay. So we have those 3 databases, which is the IQVIA Disease Analyzer Germany, the Dutch Primary Care IPSI Netherlands, and Pharmetrics Plus for academics. And in the first column, you would see the most simple analysis, where we only looked at what the unit was. And you see that the majority of drug records had a milligram unit, and they have the exact same, our dose estimates were exactly like the WHO late daily dose. In the second column, when we took into account the route, you see that in the primary care in the Netherlands, our dose formula did not have good results for the injectables, but also the number was very small. But it's relevant if you, for example, want to have, for whatever reason, use the injectables. And in the last column, we also have the dose stratified by pattern. And here you see that the milligram, the fixed amount formulation in oral is 99.6% in the IPSI database. So it would make sense to perform a study in oral tablets, for example, and not in injectables. If I have enough time, yes, I would also show the second example. It's quite an interesting one because here the WHO daily dose depends on the dose form. So it's either an inhaled powder or an inhaled solution. And here you can see that our approach by the drug strength pattern really picked up the perfect WHO daily dose depending on whether it was the powder or the inhaled solution. Also here where there were some patterns which were off, but I mean data is never always perfect. In strength, we say that we demonstrated a uniform approach towards dose finding and we validated the dose formulas. However, the dose finding process is quite slow and extensive due to clinical review. And the major obstacle we found was the quantity field, which varied a lot depending on the databases that we've seen. And this made it really hard to suggest a uniform dose formula. I mean, this is not the point to have a dose formula per database, but we wanted to suggest a generic approach. So to conclude, depending on the setting of the data, the dosing estimation worked better or worse for different formulations and routes. And we would always suggest to perform thorough diagnostic investigations before estimating dose. And this can certainly be done with this package that the great team wrote in Oxford. And it's a drug utilization R package developed under DARWIN EU. And with that, I would like to thank the funders, collaborators, the community, the whole team in Oxford, data partners who have run the study. And if you want to know more, you can find me at poster 502 in the break. Thank you.
All right, next up, we have Chao Peng, who will be presenting generated synthetic electronic health records in OMOP using GPT.
Hello. Thank you so much for the nice introduction, Davera. So it's super exciting to talk to you guys about the work generating synthetic electronic health records in OMOP using GPT. I'm actually going to go through quite a lot of slides, so I'm going to be talking at lightning speed. All right, so why is the synthetic EHR data important? Well, the fundamental issue is that we can't share the private patient data with external collaborators. Therefore, having good synthetic data will enable or speed up certain EHR research areas, such as external validation of machine learning models or phenotype algorithm, so on and so forth. So the common approach for generating the EHR data is as follows, where the longitudinal EHR data is first converted to a data matrix using the bag-of-word approach, essentially counting the number of features in a time window. Then the GAN model is trained to generate a similar data matrix. Although this approach works pretty well, the underlying data structure doesn't capture any temporal dependencies, therefore limiting its use. Due to recent advancements in deep learning, people started operating on longitudinal EHR data directly using a combination of sequence models and GANs. This is one of the good examples. In this paper, the authors created a hierarchical model where they first predict the timestamp given what's come before, timestamp of the next visit given what's come before, and then predict the diagnosis codes based on the timestamp and the previous hidden state. Although such methods seem to have captured temporal information, it is still not sufficient because all the visits are assumed to end on the same day as the visit start dates, which is not true for the inpatient visits. There's no visit type, there's no discharge type in the sequence, and in addition, the synthetic data is not ready for dissemination for use. So, we think this problem should be tackled from a different angle. Instead of focusing on models, we created a patient representation that not only retains the patient timeline, but also captures essential visit information. This representation is designed to have the demographic prompt at the beginning, followed by a bunch of visit blocks. The key innovation here is the use of so-called artificial time tokens, or ATT, to represent the time intervals in days between visits or within the inpatient visit span to preserve durations. That way, we can seamlessly convert this sequence to OMOP back and forth. So based on this idea, we proposed a framework where we first convert OMOP to a bunch of sequences using the patient representation. Then we train a generative model to learn a sequence distribution and generate new data. Next, we convert the synthetic sequences back to OMOP using the OMOP converter. And finally, we evaluate the quality of the synthetic OMOP using all these tools and philosophy. So for the generative model, we use GPT due to its recent success. The key idea is to treat the patient sequences or history as if they were text documents. So at the input layer, we use concept embeddings plus the trainable positional embeddings. In the model, we use 16 transformer decoders, and we train the model using next token prediction. To generate a new sequence, we randomly draw a patient from the population and turn it into a demographic prompt and feed it into the model to autoregressively generate a sequence. So when sampling from the output distribution, there are top K and top K sampling strategies, which is essentially a hyperparameter to control the shape of the output distribution. We tested a few options such as top K equals 100 or top P equals 95%, and for each strategy, we generated 500,000 patient sequences. So because we know the pattern in the representation is always the demographic prompt followed by a bunch of visits, so we can easily convert this back to OMOP records. The most important thing here is that because we have a starting point, the year token in the demographic prompt, we also have all the time intervals embedded in the sequence. This allows us to calculate the timestamp accurately for any token in the sequence, which is how we reconstruct the patient timeline in OMOP. Okay, now we have the synthetic data. How do we know it's good? Or in other words, how do we actually measure the similarity of the two OMOP instances? So we came up with this evaluation where the synthetic data is evaluated on 3 levels. On level 1, we look at the concept distributions in different groups, such as full population or female population. On level 2, we look at the co-occurrence relationships within the synthetic data. And on level 3, we're going to run logistic regression model on synthetic cohorts. So what we are looking at here is the comparison of the concept prevalence stratified by population in rows and by domain in columns, where the x-axis represents the source data and y represents the synthetic data generated using the top P95% strategy, and each dot represent the concept in the plot. So what this shows is that the majority of the concepts are actually landed around the diagonal lines in the plot, suggesting the synthetic data agrees with the source, especially in the high frequency regions. Okay, so on level 2, we're going to compare the co-occurrence matrices of the source and synthetic OMOPs. We first construct the lifetime co-occurrence matrix and then simply calculate the KL divergence between them. We also included a lower bound and upper bound. So the lower bound was obtained by applying the same procedure shown on the left to 2 randomly drawn samples from the source. And for the upper bound, we first generated a hypothetical co-occurrence matrix by assuming independence in the source data, and then applied the same procedure to obtain the upper bound. So this is the results of the KL divergence associated with different sampling strategies, including lower bound and upper bound. So basically, the closer it is to the lower bound in the bottom left corner, the better the synthetic data. And in this case, top P95% seems to be the best strategy. Okay. On level 3, we'll test whether the synthetic data carries the same machine learning capability, meaning if we generate a synthetic cohort and run logistic regression on it, it should have a similar performance as the real data. We included 5 different cohorts that we previously used in the work called Sherbert. Not going to go through the cohort definitions in the interest of time, but the hope is that we're going to include more cohorts in the future. The more, the better. So here's the results. In each cell, we report 3 numbers, the prevalence of the positive cases, ROC AUC and PR AUC. The second column of the table, highlighted in green, shows the ground truth metrics generated from the real data. And the other columns show the metrics corresponding to different synthetic data sets. Unfortunately, we don't have time to go through the results, but the take-home message here is that we are able to replicate the model performance using synthetic data for every single cohort. In conclusion, this is the first deep learning framework that generates longitudinal synthetic data using OMOP. Secondly, we created a patient representation that allows us to reconstruct the patient timeline without any loss of temporal information. And finally, evaluation procedures show that the synthetic data preserve the underlying characteristics of the real population. I'd like to thank my team and the collaborators for your inspiration and your support. I'd like to take any questions during the poster sessions at poster 503. And thank you very much.
Everybody's staying in their time frame. It's really, really impressive. So now I'd like to introduce Tom Seinen, who will be presenting comparing concepts extracted from Dutch text to conditions in the structured data.
Thank you, Davera, for the introduction. Yeah, so we stay in the realm of data similarity because I will talk about comparing extracted concepts from text to the structured conditions in the database. Because at the Erasmus Medical Center, we maintain a large Dutch general practitioner database of 2.5 million patients. That is around 8% of the Dutch population of active patients. And while the structured data in the CDM is of course used for all kinds of studies and analyses, the unstructured text, the free text, or the unstructured data, the free text, that it sits in the notes table of the CDM, which is actually very large, 35% of the physical size of the database is unused. There's a lot of potential information unused. So to change that, we thought, okay, can we extract this information? Can we extract all the clinical concepts from the text and then use it in our analyses? So there are many tools to do this for English. However, there are not many tools to do this for Dutch. So I thought, okay, let's create a framework ourselves for extracting these concepts. So that's what we did. However, Dutch is similar to English in certain ways, but we still wanted to verify if our concept extraction was actually any good. So could we evaluate it? But that requires an annotated data set. So you do have multiple English data sets that are annotated with concepts, but that does not exist for Dutch, unfortunately. And creating one is a very laborious task, so I didn't want to do that. So we thought about this challenge and thought, okay, what information do we actually have for these nodes? Because these nodes do not exist by themselves in the database, because they often are linked to or occur together with a structured code, so a condition, for example. So then we thought about, okay, can we maybe use this structured data for evaluating our concept extraction, using the structured data basically as surrogate annotations to use it in the evaluation. And to do this, we thought, okay, can we just compare all the codes that we extracted, all the concepts that we extracted, with the structured code? Because if we can find similar or related concepts in the text, then the extraction works. And of course, the concept can be the same. So for example, if you find COVID-19, for the condition COVID-19, you find COVID-19 in the text, that's the same condition. You can also find SARS-CoV, that's a bit less the same. You can find a vaccine, well, that is related. You also find the word car or the concept of car. Well, I don't see how you can connect those two. So we made our extraction framework using an existing open source framework called MedSpaCy. And we basically changed the structure of the algorithm by using a Dutch tokenizer, using SpaCy, a Dutch SNOMED CT dictionary for the concept extraction, and Dutch context rules for seeing if we can find any negations, for example. And of course, we stored all the information again in the node NLP table. Now, for the experimental setup, we looked at the most frequent, the 300 most conditions in the database. And for all these conditions, we took all the condition occurrences for all the patients, so that's around 30 million occurrences. Then we took all the nodes within a 3-day window around these occurrences, so that's 110 million. And then we extracted all the clinical codes from these nodes that ended up like 430 million extracted concepts. Now, I said the assumption was that the text is related to the condition. Well, that might not be always right. Of course, there's always cases where the condition doesn't need any explanation, so there is no text. And of course, we're now only looking at conditions, so text can also be about procedures, medications, or other structured data. So that is could not be relevant. So we still needed some ground truth. So that's why we annotated a set of 2,000 code observations or code occurrences, including 200 different conditions. And while you would normally annotate this text with saying, okay, here's this concept, here's that concept, here's that concept in the text, we now just said, okay, does this text describe a similar concept or a related concept? So this was very fast because it is just 2 yes or no questions, so that 2 in this code occurrences annotated was done pretty fast. Now, to calculate the similarity between concepts, we decided to look at pre-trained concept embeddings, snowmed embeddings to be exactly. So these embeddings are created using a neural network and are a numerical representation of a specific concept and therefore hold a certain semantic information of this concept. Then, to calculate the semantic similarity between the concepts, we could use the cosine distance between the embeddings. So, for example, COVID-19 and SARS-CoV have a distance of 0.87, and COVID-19 and CAR only 0.01. Now, to quickly say, okay, are the concepts that we find in the text, are they related to the condition? We just look at the concept with the largest similarity to the condition, just to make it quick. So we only focus on the concept with the maximum similarity. However, you still have only a number. So how do you say, okay, this concept is the same, or this concept is similar, or it's related? Therefore, we looked at the distribution of all the different 400 million extracted concepts that we found. We made a distribution of them, and then started looking at both the distribution and examples to see, okay, what kind of thresholds can we use? So for the related concept, we thought, okay, everything above 1 standard deviation of the median, those look related, and everything above 1 standard deviation from the max, so minus the max, those are actually quite similar to the original condition. Now, if we then used these same thresholds on only the maximum similarity concepts, we could then see, okay, in how many cases does the text describe the same condition as the structured data? So here we see that for the 30 million condition occurrences, that in 27% we find a similar concept, in 47% we find a related concept, and in 27% we only find unrelated concepts unrelated to the condition. Now, we also evaluate this on the annotated data set. So here on the left you can see the observed, so that's the annotated data set, and on the right is the predicted data set with the unrelated, related, and similar concepts. And here we find that in the 2,000 occurrences, we found less similar concepts than we actually expected, but we did find more related concepts than we expected. We also find a bit more unrelated concepts than we expected. However, if we did not find a similar concept, then usually a related concept was found. So that was pretty nice. And if we look at this problem as a classification problem, then we can see that the related concept is quite good, better than getting a similar concept, but combining the both, then we have a pretty good performance. Now, in conclusion, we created a non-English extraction framework that we evaluated using the structured data. Of course, there are some limitations, but it is symbol and language agnostic. Our framework performs relatively well. And we found that our assumption was quite true, that the related and similar concepts are found in the surrounding text of the clinical conditions. If you have any more questions or if you want more information, come to my poster at 5:04.
Alrighty, to round out our lightning talks, we have Jenna Reps, who's presenting finding a constrained number of predictor phenotypes for multiple outcome prediction.
Thanks for the introduction. So I'm going to be discussing a project that we've been working on where we've tried to look into patient prediction and see whether we could identify a smallish, say around 50, predictors that could be used for any outcome. So before I actually dive into the project, I just want to highlight this is very much a team effort. And a shout out to Chung Soo, who actually managed to take all of our individual photos and put us into a hypothetical if we worked in the same office photo. So why is it that we're interested in coming up with this constrained set of predictors? Well, some of you may have come across websites like MDCalc, where you can actually go onto there, you can pick a model you're interested in, you can fill out things like your age, your sex, and a few questions about yourself. Press enter and it will tell you your risk of a certain outcome. But what you find with these is this will give you a risk of one outcome. If you wanted to see your risk of another outcome, you have to find another form, fill out a few more questions, press the button, and you get that risk. But this doesn't scale up. If you wanted to know what's my risk of actually 100 different outcomes or 1,000 different outcomes, and in Odyssey, we like to do things at scale, maybe even 1 million outcomes, you're going to have to fill out a lot of different questions, and it's going to be a lot of forms. So our idea is, can we find some predictors that are just generally good for any prediction task? And that way we could have one form that you fill out, press enter, and it could tell you your risk of many different predictions. So the methodology, there's quite a lot to it. And if you want to hear more detail, I welcome you to come find me at poster 505. But just to give you a brief overview, we ended up doing a very, very large scale characterization. So what we did is we looked at lots of different prediction tasks. And within each prediction task, we looked at what drugs and conditions were recorded in the year prior to index. And then we looked at which of these drugs and conditions were associated to developing an outcome in the future. Because for prediction, the good predictors are generally the things that are strongly associated to having the outcome in the future. So we looked at, let's find these drugs and conditions that are associated that should be good predictors for an outcome. But let's not do this for one task, let's do this for 65,000 prediction tasks. So we looked at many, many different at-risk populations, many, many different outcomes within lots of claims and EHR data sets. And we counted out of these 65,000 plus prediction tasks, how often each drug and each condition was associated to developing the outcome in the future. And we ordered these drugs and conditions in descending order based on how often they were found to be associated. So these conditions and drugs that were in the top 1,500, these are the things that generally, over lots of different prediction tasks, are good predictors. And we reviewed them and we found 67 different topics, things like hypertension and heart failure, that we then created phenotypes for in the standard Odyssey process. So this is our list. I'm sure some of you may not be able to read if you're at the back, but there's a list online, and also I'm happy to explain them more at the poster. But effectively, there's 3 takeaways from our 67 predictors that we found, or candidate predictors. One thing I want to highlight is that they're available in the phenotype library, so you can actually get them from an R package now that Galpham is maintaining. And then secondly, these predictors, they actually are quite diverse. So we're seeing that we actually found things that cover lots of different disorders. So that's good. And secondly, they're things that are commonly recorded in our data, and often you'll find these in existing prediction models. So really, we didn't find anything new. We just found a set of 67 predictors that you would expect probably are going to be good predictors in models. The next thing we wanted to do, though, was seeing how well did these do. So our previous approach of doing prediction in Odyssey is the kitchen sink approach. You use any drug, any condition that were recorded in the prior year to see if you can put them as candidate predictors plus age and sex, and then you try and develop a model with those. So this is what we've called our best case logistic regression. Throw everything in there and see how well we do, no constraint. And then we've got our models that we develop using our constrained set of predictors, the 67 predictors that we just identified plus age and sex. So these are our constrained models. And then we also decided, well, we'll actually look at some prediction tasks where we have existing models, and we can see if there's how the existing models do as well. So the example I'm showing you here is the 1-year risk of mortality. And in that prediction task, Charlson comorbidity index is a common one. So we put that in. So there's a plot here. This is just one example, so one prediction task. But if you want to see more, come find me at my poster. The first row here is the best case. This is the unconstrained. So this is a model where we've got tens of thousands of predictors that we could have in that model to predict mortality in the next year. The second one is just age and sex only predictors in the model. The third and fourth row, this is the constrained models. So this is when we're just using our 67 predictors we just found, plus age and sex. And then the bottom one is the Charlson comorbidity. So this is the existing model for this task. And each column here is a different database. And the number you find here is the AUC. So this is a measure of how well the model does in terms of discrimination. The closer that is to 100, the better. So the further they are to the right, the better these dots are. And what we see in this prediction task is that our constrained models, so our models that use only 67 predictors plus age and sex, were actually doing as well or better than the model that was using tens of thousands of predictors as candidate predictors. So this is actually very promising. We saw this result across all these different databases. So for this prediction task, our constrained set of predictors actually did very, very well. And it does seem like you can come up with a constrained set of predictors that should do well. But we didn't just do it for this prediction task. We actually have this for many different prediction tasks. And as I said, find me the poster if you want to see more results. So if this is made you interested, we actually, in the Odyssey style, we didn't stop there. We actually have created a website using these 67 predictors that you can actually go to. You can fill out one form, put in your age, your sex, your 67 predictors, whether you have them or not in the prior year, and it will tell you your risk of not one, not two, but over 100 different outcomes. So I hope you enjoy the website. Thanks for listening.
Well, thank you to all of our panelists for their talks. Thank you so much. So now, our next session, we'll go into our first poster and demo session. The methodological and data standards can be found on my left, which is your right. And open source clinical lightning talks and posters will be on my right, your left, over on that side. Also, be sure to look for the 4 poster walkers who are carrying signs indicating their poster themes. So where are our poster walkers? Let's see, we've got Mui Van Zant, who's doing data standards. We have Christoph Lambert, who's doing methods research. Paul Nagy, who is, where's Paul? Oh, there. I don't see him. Oh, hello, there's, okay. Paul Nagy doing open source development. Who's doing clinical applications? Ah, there you are. Hello. Oh, it's Christian. Hello. Doing clinical applications. So have a great time in the poster demo session, and be sure to come back to your seats by about 3:30, right on time for the next Lightning Talk series. Thank you so much.